Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to discuss conditional distributions of continuous random variables. These conditional distributions allow us to update our probabilistic models when we find out the values of some of the variables within the model. By updating the probabilistic model, we mean updating our uncertainty about the remaining variables. We're also going to discuss independence and conditional independence for continuous random variables. Let's get to it. So we're going to talk about conditional distributions of continuous random variables, just to make that clear. And our goal is to learn how to update models when we find out the values of some of the variables within the model. Let's take a look at an example. So here we have our triangle lake example. In case you haven't seen the previous videos, here we have an otter that is swimming in a triangular lake that is here. And we don't know anything about where the otter might be, so we model the probability density of its location. An otter is an aquatic animal. I don't know how common otters are for wherever you're from. In Spain, they're not that common, but I digress. So anyways, this aquatic animal is on the lake somewhere. We don't know where it is. We model the density of its location as being constant within the lake. And because this triangle has area 1/2 and the density has to integrate to 1, the density within the triangle is equal to 2. All right, so now how about what would happen if I'm here, this is me, beside the lake, and I see that the otter is at coordinate 0.7, so the vertical coordinate of the otter is 0.75. So I see that the otter is there, but I don't know anything about the horizontal coordinate. How do I update my uncertainty about the location of the otter? So of course I know that that coordinate is 0.75, that's what we're assuming, but how do I update my uncertainty about the other coordinate b? A first idea, which makes a lot of sense, is to say, okay, the joint density kind of tells us the probability density of the otter anywhere. How about we just look at it on this line of a equals to 0.75? If we do that, we see this, which makes a lot of sense, right? Because this is exactly where the otter can be, and we know that the probability within the lake is constant, so this actually is quite reasonable. But what is the problem? Is this a valid PDF for the random variable b? Feel free to pause the video and think about it for a moment. It is not, because it doesn't integrate to 1. It integrates, if I'm not mistaken, to 0.5. All right, so in order to derive this conditional PDF, we're going to have to take a step back and reason a little bit mathematically, and then we will come back to this. Okay, so what is a density? Remember, a probability density is the probability that a random variable is within a certain interval of very small length, epsilon1, divided by the length of the interval when we take the length to 0. If you don't remember this, go check out the video on probability density functions for a single random variable. So this is exactly what we want, okay? So we want the conditional probability density of the random variable b. Oops, what am I doing there? This is what I wanted to do. Of the random variable b, given that we're conditioning on this event, that a is equal to a. So can we just take this limit? Well, we run into an issue, because here we're conditioning on an event, which is a equal to a certain fixed value, which has what probability? I wonder if I'm asking it here. Yes. What's the probability of that event? Think about it for a moment. That probability is 0 because a is a continuous random variable, and the probability that a continuous random variable is exactly at a certain point is 0. So that's problematic, because now this conditional probability is not well defined. So what do we do? Okay, it's not well defined. What we're going to do is we're going to say, okay, we cannot condition on the on the event that the random variable a is exactly equal to this value a, okay, this constant value. How about we condition on the event that it's in an interval very close to a? So in an interval of just length epsilon 2 around a, and then I don't know what I was going to emphasize there. Hopefully you get it with my gesture. And now we're going to collapse the interval by taking the limit. Oh, not yet, sorry. Okay, so we're going to do that in the next slide. We're not going to collapse the interval yet. First, this is a well-defined probability. Hopefully you realize that for any fixed value of epsilon 2. Okay, and then when we take this, this limit of epsilon 1 going to 0, that gives us the density conditioned on this event, which has non-zero probability. So that's okay. All right. Of course, this is not what we want. We want the conditional PDF conditioned on the event that A is exactly equal to that value. So what are we going to do? We're going to take the limit of this object when epsilon 2 goes to 0. So we're going to take two limits, when epsilon 1 goes to 0 and when epsilon 2 goes to 0. In order to simplify the mathematical calculations, we're going to set epsilon 1 equal to epsilon 2. And we're just going to call that epsilon. Hopefully you realize that that's okay, but it's important to remember that it's two separate limits. One of the limits, which is this one, is so that we obtain a density when we divide by the length of that interval. The other limit is going to be because we cannot condition on this event of zero probability. We have to condition on events that have non-zero probability and then take the limit to be able to obtain something that is, that captures this conditioning on A being equal to a single point. So hopefully that's clear. Again, we're going to set epsilon equal to both epsilon 1 and epsilon 2. All right, so now we have the limit when epsilon goes to 0 of this conditional density that we have just defined, where we have the conditional probability that B is in this small interval divided by the length of the interval, and we're conditioning on the event that A is within this small interval close to that value. I realize, by the way, that when I'm writing, I think it's nice that I'm calling the random variable A the same thing as the constant A, but when I'm talking, this doesn't work at all. So hopefully that doesn't get too confusing. You should always remember the squiggly lines indicate a random variable, something that we have to describe in terms of probabilities. If there's no squiggly line, those are just constants. And here what we're trying to do, just to remind ourselves, is to derive the conditional density of a random variable B given another random variable A. We want that conditional density at a point B, and we're conditioning on A being equal to that constant. All right, so hopefully that's clear. All right, so now what are we going to do? We're going to apply the definition of conditional probability. What's this conditional probability? Is just the probability of the intersection of those two events. So B is in its interval and A is in its interval at the same time, divided by the event that we're conditioning on. And now we're going to divide by epsilon up and down in order to take the limit and obtain some densities. So, we divide by epsilon up and down. Here we already had a 1 over epsilon, so we have epsilon squared here. And what did we obtain? We obtained the probability that B and A, this 2D random vector formed by A and B, are in a square of area epsilon squared close to this point AB, okay, close to that point, and we have divided it by the area of that square. Maybe I'll erase so that you see it clearer. So what is that? Maybe I'll use this instead. So what is this? The probability that you're in a square divided by the area of the square when the area of the square goes to 0. That's just the joint PDF at that point. What is this limit here? Where we're taking the probability that A is in an interval divided by the length of the interval, and we're taking the length of that interval to 0. That's just the marginal density of A. So we get this expression, which should remind you of the expression that we derived for the conditional PMF of a discrete random variable given another discrete random variable, where we took the joint PMF and we divided by the marginal. There, things were easier. We didn't have to take all these limits because we were dealing with discrete quantities, but we obtained something that is very similar. Okay, so let's go back to our example. We're going to need the marginal PDF of A, and it's instructive to compare it to the conditional. So remember that for the marginal, we have a whole video on this. You just need to integrate over the other variable. So we just integrate over B. We integrate the joint PDF, which is equal to 2 from 0 to 1 minus A, So just to be clear here, what we're doing is we're integrating over b, okay? So if we want the value at this point, we integrate there. And you see that the non-zero values go from 0 to 1 minus a, so the marginal PDF is 2 times 1 minus a. Now, let's apply the formula that we have derived. The formula, and here I want you to pay close attention. So first we need to think what we want. We want the conditional PDF of B given A. The formula tells us to take the joint PDF and fix that value of B. Okay? Maybe fix is not the right way. The joint PDF evaluated at that value of B, and we're conditioning on A being equal to a certain value. So what we do is we take the joint PDF for that value of A. I prefer to use the word fix here. We're fixing the value of A here. So essentially we're doing what we were saying before. For example, if we're conditioning on the value 0.75, A is equal to 0.75, we're considering this function, the joint PDF, as a function just of B where we have fixed A. This is what I meant where I wanted to fix A. So we're fixing A to 0.75 and we get this function of B. This is exactly the same thing that we had kind of suggested by common sense right at the beginning, but we had a problem, which is that this thing did not integrate to 1. But we have this other term. What is this other term equal to? Well, this other term is the value of the marginal PDF of A at that value, okay, at that value that we're fixing, in this case 0.75. How do we obtain that? We obtain that by exactly integrating this at A equals 0.75 over B. So it's exactly the integral of this function here. So essentially, we have derived this mathematically. We see that it makes a lot of sense in terms of densities, but we could also have derived this just by common sense saying, all right, how about we slice the joint PDF to obtain this? Now we have to normalize it so that it integrates to 1. So let's integrate it, see what we get. What we're going to get is the marginal exactly at that point, that's 0.75. And now we divide by that. All right, so again, this formula, we have obtained it with these limits and so on. It actually kind of also follows by common sense, just by slicing the joint PDF and normalizing it appropriately. And how does it look like? Well, actually here we have plugged in 2 times 1 minus a and 2 above, the 2's cancel, and we get that we have a constant PDF from 0 to 1 minus a. And here you really need to remember which is the variable over which you're computing the density and which is the variable that is just a parameter that is telling you which conditional density to use. In this case, a is just this fixed parameter. So this actually kind of makes a lot of sense. Once you know that the other is in at some vertical coordinate, the horizontal coordinate is just uniform. This is extremely different from the marginal, which has this triangular shape because it's more likely for the other to be more towards the left. But if you know the vertical coordinate, that's no longer true. The other has the same density of being at any point until, from 0 to 1 minus a. In this case, from 0 to 1 minus 0.75, which is equal to 0.25. So in general, the conditional PDF of a random variable B given a random variable A is obtained by taking the joint PDF and dividing by the marginal PDF at the value on which we're conditioning. Here, this obviously should be an A. Sorry about that typo. When we have a d-dimensional random vector and we want to condition on one of the variables having a certain value, then what do we do? No, not one of the values, sorry. On all of the values except one having a certain value, what do we do? Well, let me color this to make it hopefully a little bit clearer. So we want the probability that the ith entry is equal to b, given that all the other entries have these values. So what do? We take the joint PDF, we fix those values, okay? And and we get like this 1D function of just b, but that's not going to integrate to 1. What do we need to do? We have to normalize equivalently in this, like because of these arguments involving limits, we should divide by the marginal of the remaining variables, which is equal to this. And remember that this marginal you can obtain by integrating out b. So that's why it actually normalizes the conditional PDF so that it will integrate to 1. What if we want the conditional PDF of 2 random variables given 2 other random variables? In this case, the random variables are entries of this random vector x. What are we going to do? Again, it's very, very important to separate between the random variables over which you're computing the density and the ones which you're fixing, which you're conditioning on. So we're going to write the joint PDF, which looks like the joint PDF, but really what we're doing is we're fixing this guy and this guy, and we're interpreting it as a function of these 2 guys. So now it's like a 2D function, which needs to be normalized. And the way we normalize it is dividing by this, which is actually the integral with respect to b and c, because it's the marginal at 80. Okay, hopefully that makes sense. And hopefully you see how this generalizes to any number of variables or any dimension d of the random vector. So we have kind of already proved this, but let's make sure. Is the conditional PDF a valid PDF? It's a density, right? Like it's going to be non-negative because it's a joint PDF divided by the marginal PDF. Those are 2 non-negative quantities, so of course it's going to be non-negative. Now we want to see whether it's a valid probability density in the sense that it integrates to 1. So what happens if we integrate it with respect to the variable over which we're computing the density, which is b? We just plug in the definition. Remember that this is just a normalizing constant because we're conditioning on a particular value of a. What happens if you integrate the joint PDF over b? You get the marginal. So this will cancel out to 1. Of course, you need this density to be non-zero for this to be well defined. Okay, otherwise this is not true anymore. So we can only compute the conditional PDF at points where the density of the value of the variable that we're conditioning on is non-zero, which makes sense because otherwise that we cannot obtain those variables according to the joint PDF. Hopefully that makes sense. Just by definition of the conditional PDF as which is usually obtained. No, okay. I don't know why I said usually. So let me start again. The conditional PDF is equal to the joint divided by the marginal. So if we move things around, we can write the joint PDF between 2 random variables as the marginal PDF times the conditional. And we can do this in any order. And this is still going to hold. This is exactly the same like the chain rule for discrete random variables, except that we're using densities instead of probability mass functions. We can do this for any number of random variables, and this is how the chain rules usually work. First, we start with the marginal of one of the entries, and then we start multiplying by the conditional of another entry given that one, then the conditional of a third entry given the first 2, and so on and so forth. We always have to condition on everything that we have taken out. I like to say taken out of the joint PDF, although maybe I don't know how intuitive that is here. We always have to condition on all the other variables that we have considered before. Hopefully that makes sense. We can do this in any order. So usually when we write this out, we go from 1 to n if we have n random variables. But you can do this in any order, and it's actually very important to choose the order wisely when you're doing probabilistic modeling or homework problems or exams. All right, so let's take a look at some pictures. Here we have again the temperature at Versailles, Kentucky, and Manhattan, Kansas. Each point is an hourly measurement over a year. We already explained how to approximate the joint PDF using multi-dimensional kernel density estimation. Now we're going to take a look at the conditional PDFs. Okay, so now we're going to condition on the fact that it's -10 in Manhattan, very cold in Manhattan, Kansas. What's our uncertainty about Versailles, Kentucky? So what are we going to do? We're going to slice the joint PDF there, and we're going to divide so that it integrates to 1. How do we do that? Well, we can do a kernel density estimate of the PDF at Manhattan, okay, and then take that value and then divide, and we get something like this. Realize that this is a little bit noisy because at that point we don't have that many data. It's not that common that it's minus 10 degrees Celsius in Manhattan. Okay, so this is why the conditional looks a little bit noisy, but it's clear that the temperatures are very related, right? So this is telling us that most of the density is actually close to minus 10. It's really cold. When it's very cold in Kansas, it's also very cold in Kentucky. What happens when it's a little bit warmer? Not warm, but 0 degrees Celsius in Manhattan. Again, same thing, we slice. We have to divide by now that value so that we obtain a valid density. And, in Versailles, now the temperature is centered around 0. So we really see, you can also see this from the joint PDF, how like the two temperatures are really almost proportional, but the conditional makes it extremely clear. When we go to 10 degrees, again, we have to normalize. The temperature in Versailles is centered around 10 degrees. Let's do 20. It keeps getting warmer in Versailles. What happens if it's insanely hot in Manhattan, 30 degrees Celsius? In Kentucky, it's going to be very, very hot also. And you can see how concentrated the conditional is. This tells us that really, like, you're pretty sure it's going to be very hot in Kentucky if it's very hot in Kansas. Interestingly, for the colder temperatures, that's not as true, right? They weren't as concentrated. And that's the kind of information that a conditional density will give you. Let's take a look at another example, at the relationship between two other quantities. So here, I found this dataset online that has the box office gross, which is basically the money made by a movie. I don't know what that's called, gross income of the movie, something like that. I don't know. Against duration in minutes. We're going to see how these two quantities are related. So this is the conditional PDF. Notice that, we cannot have negative money, so that's why it's capped in this weird way. And a lot of movies make very little money, so this is why we have, a lot of density there. So now we're going to, this is the marginal. This is the marginal PDF of the box office gross. We're going to compare it to the conditionals. What happens when we slice, for example, at a duration of 90 minutes? How does that conditional compare to the marginal? And it's actually pretty similar. Now let's slice the PDF again at 100 minutes. How does that conditional compare to the marginal? So I'm plotting the conditionals here. Okay, just to be, in case you missed that, this was the conditional for 90 minutes, that's the marginal. They look pretty similar. I'm going to put them on top of each other in a moment. This is for 100 minutes, again, very similar. What happens for 110 minutes? Again, pretty similar. So if I put them all on top of each other, we see that they're not exactly the same. There's a little bit of an effect maybe where longer movies make a little bit more money. But in general, these conditional PDFs look very, very similar also to the marginal. When this happens exactly, when the conditionals are exactly equal to the marginals, here this is real data, so that's rarely going to happen. But, if that happens exactly, then we have independence between random variables. So intuitively, what does it mean for two random variables to be independent? It means that the events that a random variable is in a certain set is basically the probability of an event of the random variable being in any set. This Borel set, again, it sounds fancy, I keep saying this is just a union of intervals. So in any reasonable set, the probability that a random variable A is within that reasonable set, conditioned on the value of the other variable, basically changes nothing. Okay, it's always the same as this marginal probability of A being in that set. In order for this to happen, the CDF, the conditional CDF of A given B, has to be equal to so what is that CDF equal to? It's a probability that A is smaller than a certain value conditioned on the value of B. That has to always be equal to the probability that A is smaller or equal to B. A is smaller or equal to that constant. Okay, if that happens, you can prove that this will also happen. Clearly, the implication in this direction is easy. The implication in that direction is also kind of easy because we can always express these probabilities of being in an interval in terms of the CDF. Okay, we saw that when we looked at the CDF of individual continuous random variables. What is my point here? My point is that if the joint CDF, if the conditional CDF is equal to the marginal CDF for every value of A, then we know that this is going to be true. The two random variables are going to be independent in that sense. The probability that A is in whatever set is not affected by any information about B. And equivalently, if we take derivatives, the conditional density is going to be equal to the marginal density. And this is what we observed approximately for the money the movies were making against the duration that the duration of the movies, at least within a certain range of durations. So we say that two random variables are independent if for any values we have that the joint PDF is equal to the product of the marginals. This comes from the chain rule, right? Because usually here we would have to have the conditional PDF of B given A, but under independence, that is just equal to the marginal. Same thing for a random vector or multiple random variables. We say that the entries of a random vector are independent or mutually independent if the joint PDF of the vector completely factorizes into a product of all the marginals for all possible values of the entries of the vector. All right, let's take a look at another example. Now I'm plotting the temperature at Versailles, Kentucky against the temperature at Corvallis, Oregon. This is the joint PDF, and this is the marginal distribution of the temperature in Versailles, Kentucky. I don't know how people in Kentucky pronounce Versailles. I was actually going to look that up, and then I forgot. I didn't have time. If I remember, I will tell you maybe in another video where Versailles also appears. Anyways, so what happens when the temperature at Kentucky is equal to 5 degrees? We slice the joint PDF here. We fix Kentucky equal to 5 degrees. We divide, we normalize appropriately. And now we're going to compare the marginal with the conditional. And we see that the marginal and the conditional are very different. And we see this from the shape of the PDF. It's clear that there is some dependence between Corvallis and Versailles. When it's warmer in Corvallis, it's also warmer in Versailles. So to make that even clearer, when it's 15 degrees Celsius in Corvallis, we see that it's warmer in Versailles, that it starts concentrating around warmer temperatures. The dependency is not as strong as between Kentucky and Kansas because Oregon is farther away. We're going to see a map in a moment. Now, if we see when it's really warm in Corvallis, it's really warm in Kentucky. Okay, here the dependency is actually relatively strong. Okay, so what have we learned? We have learned that Versailles and Corvallis are definitely not independent. Now let's see what happens if we also happen to know the temperature at Manhattan. Okay, Manhattan, Kansas. So how are we going to compute we're going to compute the joint PDF of Versailles and Corvallis given Manhattan. We apply this formula where we fix the variable that we are conditioning on, okay, this value T for the temperature at Manhattan. And now we have a function of V and C. So this is going to be a 2D function that is going to depend on the value that we're observing at Manhattan. So this is what we see. These are the points. I also wanted to show you kind of the points that are contributing more to this conditional density, just to provide more intuition about what this conditional density actually is. So these are the points for which, so what I did here is I said, okay, how many points do we observe? For how many data points the temperature at Manhattan is between 14.5 and 15.5. And these are the data points. This is our estimate of the joint PDF, which we obtain by dividing an estimate of the 3D, the 3D joint PDF by an estimate of the marginal PDF at Manhattan, both obtained through kernel density estimation. Okay, so you can see that basically it roughly corresponds to those data points. you can also see that the shape is very different. And the shape is going to be very important. What happens if, okay, so now we're going to see if apart from conditioning on it being like 15 degrees Celsius in Manhattan, we condition on Corvallis on top of that. So now we're saying it's 15 degrees in Manhattan, it's 5 degrees in Corvallis. We compute the conditional PDF of Versailles given that. What are we doing? We're again slicing this conditional joint PDF once again, fixing Corvallis to be 5 degrees. And what we observe now is that the conditional just given Manhattan is actually pretty similar to the conditional given Manhattan and Corvallis. So if we know Corvallis, if we know that it's 15 degrees Celsius in Manhattan, knowing that it's 5 degrees Celsius in Corvallis does not change our uncertainty about Versailles very much. What if we know it's 15 in Corvallis? So now we're taking another slice of this conditional joint PDF. The change again is not very big. And you see why, because here, when we're slicing like this, all of this, because of the shape of the joint CDF that is, not a circle, but, approaching a circle, those slices are actually very similar once you renormalize them. So this indicates that there is some independence in here. We'll make that a bit more precise in a moment, or maybe I can just give it away. It seems that Corvallis and Versailles are conditionally independent if we know Manhattan. And this is reflected in the conditional joint density. So what happens if it's warmer in Manhattan? So these are the values for which the temperature at Manhattan was close to 25 degrees. If we compute the conditional joint PDF, notice that it looks extremely, very different to the other one. Okay, this is the conditional joint PDF of Versailles and Corvallis, given that in Manhattan it's hotter. So before we're taking something like this, now we're taking something like that. What happens to the conditional distribution of Versailles given Manhattan and also Corvallis? So this is the conditional just given Manhattan. Now we're going to slice this conditional joint PDF to get the conditional given Manhattan and also Corvallis. And what we observe is that it's actually very similar to the marginal given Manhattan. So this means that once we know the probability in Manhattan, again, Corvallis does not really provide a lot of information. If we slice this thing, we obtain pretty similar conditional distributions. Here you see it again for 25. The conditional again looks pretty similar to, so the conditional given Manhattan and Corvallis looks very similar, which is this one, looks very similar to the conditional given just Manhattan. When this happens completely, all of those conditionals are the same, we say that the variables are conditionally independent. But before that, I forgot that I wanted to show you the location of these places. So this is Manhattan, Kentucky, this is Corvallis, and what we're saying is that if you know what's going on here gives you very little information about the temperature here, which makes a lot of sense. So conditional independence is essentially the same as independence, except that we condition on the value of a third random variable, okay? Otherwise, it's exactly the same thing. We say that two random variables are conditionally independent given a third one if their joint PDF given that third random variable factorizes into the conditional marginals, because here, otherwise, by the chain rule, we would have to also condition on A. But those conditionals, as we saw in the case of Manhattan, Versailles, and Corvallis, are all the same if we have conditional independence, so that's why we can just write the marginal there. Same thing for random vectors or multiple random variables. So here we say that these D1 random variables are conditionally independent given a random vector. So this is a random vector of dimension D2 if their joint conditional PDF factorizes into the individual marginal conditional PDFs given Y, okay? You always condition on Y, all right? So what have we learned? We have learned how to compute conditional PDFs, and we had to derive them kind of from common sense. You can just slice the PDF and then normalize it. But we also saw that this is mathematically sound. Okay, we took all of these limits and we derived the definition of the conditional PDF, and we obtained essentially that same approach where we just slice the joint PDF and normalize it appropriately. We defined independence and conditional independence for continuous random variables, and we worked through a couple of real-world examples where we see this structure. And that's it. That's all we did. Thank you very much.